Usually when a massive multi-million-dollar engineering project fails, it's this spectacular, undeniable event. Think of a suspension bridge collapsing into a river.
Right, it's highly visible. It's physics.
Exactly. You get the twisted metal, you have structural engineers pointing at a snapped tension cable, and there's a definitive incident report that says, look, right here, this is exactly what went wrong.
You can trace the failure back to one specific stress point or a miscalculated load bearing.
Yeah, but when you step into the world of artificial intelligence, that visibility just completely vanishes. We're looking at a landscape that is, honestly, it's a massive invisible graveyard.
That's a great way to put it.
I mean, the year is 2026, and AI is deeply embedded absolutely everywhere. It's in your phone, your CI/CD pipelines, your customer service backend.
Literally everywhere.
Yet right behind that shiny curtain is a ghost town of incredibly expensive enterprise AI projects that just quietly died. No alarms, no twisted metal, just abandoned repositories. So, welcome to the deep dive.
Today, we are opening up the 2026 edition of AI Systems Engineering by Jens Belner.
And our mission for you today is to bridge that brutal gap between a machine learning model that looks, beautiful in a Jupyter notebook and a robust, hardened AI system that actually survives the sheer chaos of the real world.
Because the wild is unforgiving. We're going to unpack the silent killers of AI, the wild inference costs of large language models, and the hardcore engineering wizardry keeping these systems from collapsing.
Okay, let's unpack this, because Belner hits us right out of the gate with this shocking statistic. A Gartner 2025 survey found that 58% of enterprise AI projects never even reach production.
That is wild. More than half?
Right. And of the ones that do make it, 30% are actively retired within 18 months because of runaway costs or reliability issues. Just how does something so smart fail so frequently?
Well, it's because the industry has suffered from this fundamental misunderstanding of what an AI system actually is. People, especially executives, tend to think the algorithm itself is the entire product.
Like you just build the brain and you're done.
Exactly. You train the weights, you get a good benchmark, and boom, you ship it. But Belner lays out these 3 core principles, his 3 laws of production AI, that completely shatter that laboratory mindset.
Okay, what's law number 1?
Law number 1 is that production is the only test that matters. Offline evaluation is essentially a closed-book test on yesterday's reality.
Yeah.
It can never capture the sheer entropy of live users.
I mean, building an AI model is like building $1 million Formula One engine. It's an incredible marvel of engineering, right?
Oh, absolutely.
But if you just drop an engine on the track without building the chassis, the transmission, the telemetry sensors, and hiring the pit crew to change the tires at 200 miles an hour, that engine is just a very expensive, very heavy paperweight.
The engine alone cannot win a race. Which leads directly into Belner's second law. Infrastructure is the product.
Okay, so not the model itself.
No, the neural network is just a tiny, fragile node sitting in the middle of a massive data pipeline. Data ingestion, real-time feature calculation, dynamic routing. That totality is the product you are actually shipping.
What?
And the third law is probably the harshest reality check for any software engineer. Everything degrades. If you deploy a production AI system and leave it completely alone, it will inevitably rot.
Okay, I want to push back on that idea of rot for a second.
Yeah.
Because if I write a standard deterministic sorting algorithm, it works forever. Math doesn't just stop working.
Right, a sorting algorithm is static.
So if a data science team gets 98% accuracy on a validation data set in the lab, how does it physically break when it hits the real world?
What's fascinating here is what Belner calls the accuracy illusion. The root cause of this illusion is a phenomenon known as distribution shift.
Distribution shift?
Yeah. When you evaluate a model in the lab, you are using a specific static data set. You've curated it, you've cleaned it, but production data is messy. It's unpredictable and constantly drifting.
So the data changes, not the model.
Exactly. The statistical distribution of the data the model was evaluated on simply doesn't match the distribution of the data it encounters in the wild.
It's like training a computer vision system to recognize flawless, studio-lit photographs of cars. It gets 99% accuracy.
Sure.
Then you deploy it to a traffic camera on a real highway where the lens is covered in freezing rain, mud, and glare. The mathematical weights inside the neural net are totally fine, but the inputs have fundamentally shifted.
And because it's not a visible bridge collapse, this degradation happens entirely in the shadows. Belner breaks down exactly how these silent killers operate. It doesn't happen with a flashy error message.
Here's where it gets really interesting. It's insidious. Unlike a normal software bug that crashes an app, a degrading AI model keeps running perfectly, but it just confidently gives you terrible, wrong answers. Let's dig into the actual mechanics of how models rot from the inside out.
Starting with training serving skew.
Right, and this isn't even about the outside world changing. This is a self-inflicted infrastructure wound. It happens when the logic used to compute data for the training environment differs subtly from the logic feeding the live serving environment.
So imagine you have a feature calculating a user's average transaction value over the last 7 days. During the training phase, a data scientist writes that extraction script in Python pulling historical batch data from a warehouse.
Makes sense.
But for live millisecond latency production, a back-end engineer rewrites that exact same logic in Java to query a streaming database.
And if those two languages handle null values differently, or if one library defaults to UTC while the other defaults to local server time, the live model is suddenly receiving wildly incorrect numerical distributions.
Exactly.
If you're running a high-frequency algorithmic trading bot, a tiny time zone calculation mismatch between Python and Java means your model is trading on ghost data. You could hemorrhage millions of dollars in an afternoon, and the model's health dashboard will show absolutely zero software errors. The CPU is humming along.
Everything looks green. If we connect this to the bigger picture, this is why modern organizations must use a feature store. It's a single source of truth translation layer.
So you don't have two teams writing the same logic.
Right. Instead of having separate teams write separate logic for training and serving, the feature store ensures the exact same transformation code is compiled and executed in both environments. It physically prevents that training-serving skew.
But even if your internal infrastructure is flawless, the outside world still changes. And that brings us to data drift and concept drift.
These are crucial to understand.
If you're building systems right now, you really need to understand the mechanical difference here. Data drift is when the fundamental inputs change, but the underlying rules of reality haven't. Say you launch an e-commerce app in a new country.
Right. The demographics shift, new languages, different device types. The model is seeing data it hasn't mapped yet, so its confidence just drops.
Concept drift, though, is much more severe.
Oh, absolutely. That happens when the actual rules of the world change. The relationship between the input and the target variable completely fractures. Belner details this brilliant case study from Capital One that illustrates this perfectly.
The fraud detection one.
Yes. They were running massive fraud detection models across billions of transactions.
And the models started silently degrading. Not because the code broke, but because fraudsters are, highly incentivized innovators.
That's smart.
The criminals realized Capital One's models were catching specific velocity patterns, so they introduced concept drift on purpose. They started spoofing geolocations, utilizing synthetic identities, spacing out transactions in novel ways that the historical training data had never seen.
And the massive problem for Capital One was their retraining cycle. In traditional ML, you wait for ground truth labels. You have to wait for customers to literally call in and say, hey, my card was stolen.
Which takes weeks.
Right. By the time the data science team manually pulled the new labels and retrained the model, the fraudsters had already moved on to a new tactic. They were constantly a month behind.
So Capital One shifted to a production-first mindset. They built an automated monitoring system that didn't wait for ground truth.
How did it work?
Well, instead of waiting for chargebacks, it tracked the statistical distributions of the model's predictions in real time. If the model historically flags 2% of transactions as fraud, and suddenly, at 3:00 a.m. on a Tuesday, it starts flagging 8%.
Or if the internal confidence scores suddenly cluster around complete uncertainty instead of being highly confident.
Exactly. The system fires an alert instantly.
They use statistical distance metrics like KL divergence to measure the shape of the live predictions against the shape of the training predictions.
By monitoring the output distributions, they caught the drift instantly. It cut their adaptation time from 6 weeks down to 72 hours. That single infrastructure upgrade saved them an estimated $40 million annually.
All because they stopped waiting for the bridge to hit the water before reacting. Now, the exact same distribution shifts that were breaking fraud models back then are breaking large language models in 2026.
But the engineering challenges and the financial stakes are exponentially higher now.
Oh, completely. The economics of LLMs flip traditional software engineering on its head. Historically, you paid for server uptime. If a user clicked a button 10 times, it didn't really cost you any more than if they clicked it once.
But with LLMs, you were charged for compute inference, usually priced per token.
Right. And a token isn't just a word. It's a chunk of computation. When you start talking about massive context windows, like feeding an LLM an entire 50-page PDF and asking it to analyze it, the token count explodes.
The context window bloat directly translates to massive inference latency and astronomical cloud bills. You build a cool internal tool, adoption goes viral within your enterprise, and suddenly the CFO is looking at an AWS bill that looks like a phone number.
Yeah, that happens a lot. And beyond the sheer cost of the tokens, you have the hallucination problem. LLMs are non-deterministic, probabilistic engines. They just want to predict the next most likely token.
Right. If they don't have the factual grounding, they will confidently invent a completely plausible-sounding reality, which is an immediate non-starter for enterprise compliance.
Which is exactly why retrieval augmented generation, or ARG, is the foundational architecture now. But Belner emphasizes that ARG is not just a simple open book test like people used to call it.
It requires serious engineering.
You take a user's query, convert it into a vector embedding, and run a semantic similarity search across a massive vector database of your internal documents. The real bottleneck is the retrieval latency and the chunking strategy.
Like if a user asks a complex question about a legal contract, how do you chunk the document? Do you feed the LLM individual sentences, whole paragraphs, or semantic sections?
Exactly, because if your retrieval system pulls the wrong vector chunks, the LLM just generates a flawless, highly articulate wrong answer.
And passing all those retrieved vector chunks into the LLM's context window consumes massive amounts of tokens. Which brings us to this incredible case study from Salesforce and their Einstein AI.
Oh, this is a great one.
They had a feature that was processing 2 million documents daily through GPT-4. 2 million. They were using it for data extraction and classification, and the token costs were just completely unsustainable.
But they couldn't just turn the feature off. So they engineered a brilliantly simple yet highly effective solution. A semantic routing architecture.
They realized that not every document requires the sheer intellectual horsepower and the massive inference cost of a frontier model.
Right. They built a lightweight classifier to act as a traffic cop. When a document comes in, the router parses its semantic density. If it's just a standard, highly structured invoice, the router kicks it to a tiny open-source 7 billion parameter model that costs fractions of a cent to run.
And if it's a standard extraction task, it goes to a mid-tier model. They reserved GPT-4 strictly for highly unstructured, ambiguous documents like a 50-page legal contract with nested contingency clauses.
The router calculates a confidence threshold. If the small model isn't confident it can parse the document, only then does it escalate the task to the frontier model.
By implementing this dynamic routing, Salesforce cut their token costs by 67%. And because smaller models have significantly lower inference latency, they actually improved overall processing speed by 45%.
Which is huge at that scale.
So what does this all mean? If you are an architect designing these systems, it means you wouldn't hire a world-class neurosurgeon to put a Band-Aid on a scraped knee. So why are you paying for a trillion-parameter frontier model to do a simple sorting task?
It forces a massive shift in how engineering teams treat interactions with these models. Prompt engineering is no longer some art form practiced by an intuitive AI whisperer.
Right.
In a production environment, it is a rigorous systems practice. Prompts are code, and they must be strictly version controlled.
If you're a developer listening to this, think about your own stack. If someone on your team tweaks a system prompt to make the AI sound more empathetic, they might inadvertently change the token generation patterns.
Oh, constantly. The LLM might start outputting conversational pleasantries like, sure, I can help with that, before outputting the strict JSON payload your downstream database is actually expecting.
The JSON parsing fails, the pipeline breaks, and your application goes down. And if that prompt isn't version controlled in your repository, you have no audit trail to figure out what changed and no fast mechanism to roll back to the previous working state.
It is all interconnected infrastructure.
Okay, so we've anchored the models with RAG vector databases, we've optimized the context windows, and controlled the costs with semantic routing. But Belner says the next frontier, the biggest architectural shift since the invention of the transformer itself, is moving from models that just talk to models that act.
Agentic AI.
Yes.
This is where the paradigm completely fractures. An agentic system doesn't just generate text. It plans, it executes multi-step workflows, and it uses external APIs autonomously to achieve a high-level goal.
The dominant architecture here is the react pattern reasoning and acting. It's basically an autonomous loop.
Right. The agent is given a goal. It reasons about its current state, deciding which tool to use. It executes an API call, observes the JSON response from that call, and then it reasons about what step to take next based on that new info.
It mimics human cognitive problem solving. And the business impact is staggering when it's deployed correctly. Belner cites the deployment at Klarna. They built an AI agent to handle their customer service workflows.
The scale of this is wild.
It really is.
Yeah.
The agent handles 2.3 million conversations a month, which is 66% of all their customer inquiries globally. It dropped the average resolution time from 11 minutes down to just 2 minutes.
But the metric that really proves the React pattern works, the AI's error rate was 0.3%. The human baseline in their call centers was 0.8%. The agent was not only significantly faster and cheaper, it was objectively more accurate than human operators.
Wait, I have to push back on the safety of this whole concept. Traditional cybersecurity relies on predictable, deterministic software. You can lock down a database. But an LLM uses natural language.
Yeah, which is inherently fuzzy.
If an agent has the power to act, to process refunds or modify a user's account, what happens when a hacker tries to manipulate it? Say a malicious user uses a sophisticated prompt injection to trick the customer service agent into believing they're a senior administrator and commands it to issue $1,000 in store credit.
This raises an important question, and it is the absolute leading edge of the field. Reliability engineering for agentic systems. You cannot just give an LLM an IAM role and hope it behaves. You have to implement the minimal authority principle.
Okay, traditional software engineers know the principle of least privilege.
Exactly, but applying it to an LLM requires an entirely different middleware architecture because you can't trust the LLM's output directly. You have to parse its intended actions. The agent is strictly sandboxed.
So if its job is to check order status, it doesn't get general database access.
Right. It gets access to one specific read-only API endpoint. And the middleware strictly validates the LLM's JSON payload against an open API schema before the execution ever happens. It physically cannot delete an order, even if a prompt injection completely compromises its reasoning engine.
And you have to engineer guardrails for the autonomous loop itself. What happens if the agent gets confused? What if the API returns an unexpected error code and the agent gets stuck in an infinite reasoning loop trying the same failed action over and over again, just burning thousands of tokens per minute?
Engineers have to enforce hard state machine bounds. Every agentic workflow must have a maximum step limit. If it takes more than, say, 8 autonomous steps to resolve a refund, the middleware forcibly terminates the loop, assumes the agent is hallucinating, and escalates the ticket to a human operator.
Belner also emphasizes a critical back-end requirement for agentic tools: idempotency.
Yes, you have to engineer your API so that no matter how many times an agent accidentally triggers an action, the result is the same as if it fired once.
Which makes sense. But how do you actually code that safety net into an unpredictable LLM? Let's say the agent decides to issue a $50 refund. It generates the payload and fires the API call, but there's a microsecond network timeout, so the agent doesn't receive the 200 OK confirmation.
And the LLM reasons, oh, the action failed, the user is still angry, I must try again.
Exactly. It fires the refund API a second time. If that tool isn't idempotent, the customer just got $100.
This is exactly why idempotency keys are mandatory for agentic tools. When the LLM generates the initial action, the middleware assigns a unique cryptographic hash to that specific intent.
Ah, I see.
So when the agent fires the second duplicate request, the backend system recognizes the idempotency key, sees that the refund was already processed on the first try, safely ignores the duplicate request, and returns a success message to calm the agent down.
You're building a deterministic safety net to catch the non-deterministic reasoning flaws of the AI.
Precisely. And for the highly consequential actions like executing a wire transfer or permanently deleting user data, Belner says human in the loop is still non-negotiable.
Right. The agent can do all the complex prep work, gather the context, and draft the payload. But a human operator has to physically click the approve button. You keep the permitted action space incredibly narrow and only expand it when you have hard telemetry proving that broader permissions are safe.
Bringing this all together, whether you are a systems architect designing these pipelines, a product manager defining the features, or just an end user relying on these tools to scale your own work, the core thesis of Belner's 2026 update is that AI is not magic. It is infrastructure.
It requires a relentless production-first mindset. It is simply not enough to download an open source model or ping an API and call yourself an AI company. You have to build the feature stores, the semantic routers, the distribution monitors, and the idempotency guardrails that keep that model accurate, secure, and cost-effective over years of deployment.
As foundation models, the GPTs, the Claudes, the Lames continue to commoditize, the raw intelligence of the model is no longer the differentiator. Everyone has access to the same APIs.
So what is the advantage?
The true competitive advantage will belong to the organization that has the best engineering pit crew. The team that can adapt to data drift, heavily optimize token latency, and maintain that intelligence in the chaotic reality of production.
Which brings us back to where we started, the invisible graveyards of failed AI. When physical infrastructure collapses, everyone sees it. But when an AI system degrades, it just quietly erodes your margins, one hallucinated vector chunk and one drifted data point at a time.
It's a silent killer.
It really is.
Yeah.
But here is a final thought to leave you with, something that builds on this entire evolution. We've talked about humans building the guardrails and acting as the pit crew for these agentic systems. But if agents are already successfully reasoning, executing API calls, and reading code, what happens when the infrastructure gets complex enough that human engineers can no longer keep up with the silent degradation? We are rapidly approaching a horizon where the only entity capable of monitoring the massive drifting data distributions of an enterprise AI is another specialized AI agent.
Wow. Think about a future where AI acts as the pit crew for other AI, autonomously rewriting feature logic, adjusting semantic routing thresholds, and maintaining its own infrastructure without human intervention. A completely self-healing system.
Exactly. So as you look at your own tech stack this week, think about the systems you rely on every day. Ask yourself, where is the silent degradation happening right now, completely unnoticed, and who or what is going to fix it? Thanks for joining us on this deep dive. We'll catch you on the next one.